you very much. So, honorable member of the committee, thank you for joining the presentation, for the final presentation of our research as a PhD student, which is titled Knowledge Graph from Newswire, a strategic approach to international business matching. So first we're going to introduce the problem and how we plan to solve it. After that, we're going to talk about some preliminary data set we built, and while building this data set we made some problems, and how we specifically solved about some particular problems with relationship classification, and how we also investigate the performance of on-board vector, of dimensionality reduction on board vectors, and we finally propose an ontology-backed pipeline for automatically building a knowledge graph from Newswire before we then conclude and discuss about future works. So, in introduction, we have this global market that is getting bigger and bigger, and it is becoming more difficult to find the appropriate partner in a foreign market for business development. So we think, even though there are a lot of information on the internet, on the web, it's very difficult to maybe go through all this information by ourselves and then find the right information. So we believe that if we can automatically restructure text data into a format that is more exploitable by machines and humans, we can have more insight. So then our idea is to provide a mechanism to support companies to understand like foreign markets. And to do that, we plan to build network structure from the business text, from the news text that we can find on the web. Then we will use graph learning methodology to create recommendations and get some more insight on the knowledge graph. So for that, we need three domains. The first one is natural language processing, which is tasked with making human language understandable to machines, and also machines able to handle human language. The second domain we'll need is our understanding of knowledge graph and ontologies. So knowledge graph are usually network structures used to represent real-world entities and the relationship between them. So to build a knowledge graph, we need to define a path structure to make sure the correct entities are connected to the correct entities and the right links are used between entities. So for that, we need what we call an ontology that defines the structure framework on which we build the knowledge graph. And the third, we need an understanding of graph learning, which is machine learning specifically tailored for graphs, because most machine learning algorithms they work on Euclidean style data. So the text is just one-dimensional vector with regular one-dimensional vector, or an image is 2D, can be two-dimensional regular grids, but graphs are not always regular. They are not always like regular data structures. So we need specific algorithm for them. And we have a different task type when using graph learning. We have node-level tasks, usually used to predict properties of a node. We have edge-level tasks that can help us predict whether a link exists or not. And we also have graph-level tasks that will help predict characteristic or properties of a particular graph. And in graph learning, there's also different approach, such as representation learning, which is tasked with representing nodes and the edge of the graph, for example, as a vector. So I listed here some different algorithms that do that. And we have graph neural network that can learn from the graph structure itself, and that can be used to do any sort of prediction task. And before those new algorithms came, we had previously had classic graph algorithms such as PageRank that was previously used by Google, and BFS and DFS, and also this algorithm for optimizations. So now we'll discuss the first step of the research, which is we realized the problem we posed, we don't have any data set. There's a lack of data set for business-to-business network. But in every machine learning or deep learning task, we need data set to train models and to do inference. So the first step of our research is to actually fill this gap of lack of data set. So we thought about building a network data set first. So then, yes, here the objective one. Create a business-to-business data set, and we will analyze the graph and then use graph learning mechanics to make some sort of prediction task. So here's how we end up building the first knowledge graph. We have, from the text corpus, we use open information extraction, and then we extracted triples. Triples are composed of subject, relation, and source, relation, and target. So the source is usually the object of a sentence, and the target is usually the object. So the relation is how the expression that link both of them. So open relation extraction actually subdivide the sentence of the text into noun phrase and the relationship between them. And on the other end, we use name entity recognition so that we can identify the exact entities that are in the noun phrase of the source and the target of each triple we extracted. Then we build the graph based on those two. And here we can have a look at what we call the giant component, which is the biggest interconnected nodes of the graph we obtain. We run our script on the Reuters dataset, which is a 1987 collection of newswire, very used in research a lot. And on the left, you can see some statistics. On the right, you can see some statistics of the graph, which is first, in this first graph, we only focus on 3 types of nodes, which are organizations, people, and place. So we were able to extract more than 20,000 entities on this first approach. Then we will later see some limitations and how we address them. We also spent some time analyzing the graph. So this figure is showing the degree histogram. So a degree in the graph, the degree of the node is how many links this node have, how much this node is connected. So we can see that most nodes are by themselves. This here signifies that we have at least more than 1,000 nodes are isolated by themselves. But we can see that it's rare, but you can find some 1 or 2 nodes that have more than 100 links. So it's usually influential nodes. For example, there can be influential organizations that we can find through this graph. Here we can see that this histogram shows the component size. So a component is an isolated set of graphs that is interconnected between them. So we say this is the giant component type. So we have many type of components. The most frequent type of component is a 2 nodes component. But I think we have the giant component, which is more than 3,000 entities interconnected together when we go through the protocols. And on this graph, we try to see if there's any correlation between the named entity count and how many links they have, how interconnected they are to other entities. So we can probably see that there's some sort of linear correlation between how much people talk about an entity of a company or maybe someone and how many links and how interconnected this company is. So maybe there might also be correlation where if someone is influential, influential in the graph, they are talking a lot about in the news. So we also decide on the graph we obtain, we decide to make some graph learning experiment. So the experiment we decided to do it was have a graph convolutional network, try to predict the node properties of our graph. So we built a graph learning network with two graph convolutional layer and with 100 epoch of training. We were able the network was able to properly classify the node properties, which is the type of entity we are talking about, up to 90% accuracy. So for this study, the goal was to understand business-to-business phenomenon. For that, we needed first to create a data set. And on this data set, we did some analysis and also tried graph neural network application. So then we have some limitations. So for example, in this graph, we only know the type of nodes. The type of node we have are limited by what the name entity algorithm gives us. So we want to go beyond that. We want to be able to identify the edge, and we want to also be able to not, because first we run on the vector compiler, so we want to automate the process so that we can run on any type of text. So the second part is how we can actually identify the link type without having to annotate too much with the text. So for that, we decide to use word vectors. So word vectors are actually very influential in the domain of natural language processing, because they back most of the tasks, such as name entity recognition, sentiment analysis, and even nowadays language models. So we think about how can we use word vectors to categorize the links. So one can ask, why do we choose word vectors in this age of large language models? So word vectors there are still some advantage compared to language model, which they are faster to train, lighter to store, and they can be used everywhere in any type of device. And we can isolate each vector and manipulate them without the context. So this is a brief overview of how word vector works. Usually it's about maximizing the probability of, this is the case of the skip-gram, the formulation of the skip-gram model from 1 to vec, which starts with maximizing the probability of one word appearing in the context of another word. So if we look at the bottom sample sentence, so the lighter green, it will be the context, and the node will be computing the vector for, it will be the word school, and then this first sum here is sliding through the context, and the second sum is sliding through the whole text. So if we're training on Wikipedia, it will be sliding through the whole Wikipedia, trying to find probabilities between each word appearing in the context of another. And then we try to maximize it with the softmax. So to assess our hypothesis, which is can we use word vector for relation classification, and supervised relation classification, we decide to use representation of relationships, which is we take the word vector of two words, and we try to pull them together with with different operations. And then we use different clustering algorithms to see which one is going to give us better results. So here is the relationship vector operations we use. We have the subtraction, which is very, very common. And we also decided to test on what we say equivariant operation, which is, it doesn't matter if we change the position of the vector 1 or vector 2. So this is the data we use for this experiment is from an earlier paper on word vectors with analogy dataset. So we decide to use this dataset because it has various type of relationships and many samples in those categories. So we also, on the right, we can see a 2D projection of those different relationship vectors. So from those operations, we decided to do a 2D projection, and each color represents a category. So we can, from this visualization, we can have a feeling that maybe the subtraction or maybe the subtraction absolute values might better represent relationships. But we decided to use clustering algorithm and see which one can give us better result in those representations. And then those are the results. We can observe that the Gaussian mixture model, which is this case, has the higher accuracy, just followed by the K-mean. So this is the configuration we use, either Gaussian mixture or maybe K-mean, and the subtraction operation to represent the relationship done in our research. So here, the finding of this experiment was that we use Gaussian model. We can use Gaussian mixture model or the K-mean on the subtraction operation that represents graph relationships. Then, in working with word vectors, we have to store every time we train a word vector, we have to store sometimes many files. So, and also do many calculations, but we realize that with shorter size word vectors, the calculations are faster and the size of storage is lighter. So we decided to do an annex experiment on how far we can reduce the size of a word vector without having to retrain them. And even if we use any type of dimensionality reduction algorithm. So that's the objective of this sub-studies. So dimensionality reduction have been used in on word vectors for performance enhanced algorithm. But by themselves, they're only mostly used for 2-dimensional or 3-dimensional visual representation. But in our case, we want to see how far we can reduce a word vector without compromising too much on the performance. So our setup we train a different word vectors model, which is the word vector skipgram, the word vector SIBO, and the glove on the 2006 entire English Wikipedia. And we train with different vector size from 500 to 50, with 50 as a jump. So we have 500, 450, 400, 350, and so on. And then we'll reduce the vectors and then test the performance on 2 tasks of word vector, which is word similarities and word analogies. So for word similarity, we use those 3 datasets. Word similarities is to find from one word, what other word is the most similar. So we use 3 datasets for that: the remain, simlex, and word sim. So those are the Pearson correlations. So we reduce the vector from the first 500, the green one and the reduced one, the orange one and the retrained one. So we can see where the performance really start being very degraded. So for most of them, it's only the maximum is at half. And then the second task we test for on is word analogy. So word analogy is usually trying to find analogy between two pairs of words. So for example, this is like, what is to France what Tokyo is to Japan? So usually it should give us the word Paris. So how good are the word vector at finding those analogies? So again, here's the score. The orange are the trained one, the green are the reduced one. And we see that we can go up to, from 500 we can reduce up to 150 without losing too much performance. So we can conclude that if we stay at half, we will have faster reduced vector without compromising too much on the performance. So the same for word analogy. So that will be the finding of this very small experiment. Before we go to the main part, which is describing an ontology and automating the whole process of knowledge graph construction. So the question here is twofold, like what ontology will define and how we will streamline the automatic construction of the knowledge graph. So first, like we said earlier, an ontology is the structure on which we base the construction of our knowledge graph. To build an ontology, we have to ask ourselves what we call competency questions. It's like what type of question the knowledge graph will be used to answer. So in our case, we want to understand business networking, so business-to-business relationship. So the question we want to ask is, for example, who, in the sense of what person or company produce a particular product, or who is buying or consuming a particular product, or what type of relationship we have between two companies, and maybe what are the people who are related to one company and so on, and also where a company operates. So we came up with the list of relationships and entity type we'll be interested in. So product is the new one, which is not supported by most named entity, but we have to train and configure our own named entity on that to be able to recognize the products. And we also have the type of relationship that two type of entities have. So if we're talking about the relationship between product and organization, it will be either producer or consumer relationship. So this is a sample graph of how, based on this ontology, the sample of knowledge graph we can have. So this is the type of entities and the type of relationship we can have. And to automate the pipeline, this is what we think will help us if we have a processing step, and then the processing step will just remove every unnecessary content if we take data from the web, and then we extract the triplet, but this time we recognize entities before we do open information extraction, and then we also filter the type of relation we have, and also using the word embedding, we justify with the previous experiment that we use word embedding to categorize our relationship. Using that, we can have the relationship categories. So I'm running out of time. So this is just a pseudocode for the triplet filtering. If we have any question, we can come back on this one and discuss more. And we also came up with a heuristic for entity linking, because in a text, a same entity can be referred to as different name. Like for example, if you take Ritsumeikan, in the text they can say Ritsumeikan, they can say Ritsumeikan University. So we have to make sure it's the same entity that we refer to avoid duplicates. And so to give an idea of how the pipeline flow works, this is we take a sample text from the Reuters corpus, and then we'll show maybe a small animation of how this process works. So first, we identify named entities. So in this case, the blue one are the companies, the green are the place, and the red are the products. Then we also do co-reference resolution, which is co-reference means that some, not a different name, but some other word refer to some named entity. So in that case, we can see that the word it refers to this company here. And every time we see the company, it refers to the same company. So for the entity linking, for example, we have computer terminal system Inc. and computer terminal, but we have to make sure that we're talking about the same entity when building the graph. So this is the task of entity linking. But also, when we will have open information extraction, sometimes it will use the company as the subject. So we have to make sure the word, the company, is referred to computer terminal system Inc. After that, we do entity linking, like we just don't like maybe put together the different names that refer to the same entity. And then we use the open information extraction will give us raw links with the raw text. But now we use the word embeddings to classify based on our ontology. So all those relationships will be categorized according to the relationship we want in our ontology. So after going through the whole process, this is what the graph will look like. So I think here we see a more interconnected compared to the previous one. It is more interconnected, and then we have the product that we see as here. And as a matter of fact, is how we can evaluate the process. Of course, it will be difficult to evaluate the graph with numbers. So, and in our case, it's not end-to-end, it's a pipeline. So every step has to be evaluated, like the name entities and the reference resolution. But we refer to the evaluation of the model we used, but in building the graph, we came up with some specific mechanisms, such as the name entity linking, the entity linking rather. So our entity linking heuristic in our on the data on the right data set, it gave us an F1 score for 0.82, which is pretty decent. And the relation categorization and classification approach gave us a 84% unadjusted random score index. So, which can be decomposed in how on each category of relationship. On the organization person type relationship, we have 86%, and on the organization and product type of relationship, we have 82%. But operate, we cannot classify because only if we see organization and place, it's automatically assigned to operates. So this is another final view of the pipeline. So from the text, we can also separate the automatic construction in two steps, which is to identify entities and to maybe relate the entities. So to identify the entities, we again go through what we have been describing. So first, name entity, link the entities, and tokenization is a small step that have to be done before the co-reference resolution to be effective. And the relation classification part is relies on open information extraction and extract rows frequency. And we use name entities, word embeddings, and the heuristic we came up to extract, to classify the relationships. And then we have our graph. And we also perform an ablation study to see maybe if we don't use the co-reference resolution, for example, or the name the entity linking steps, which were not present in the previous build, how it will affect the graph. So we see that there's a growing number of entities, which simply means like there's a lot of duplicates. So So using both the reference resolution and the entity linking help us make sure we have entities that are uniquely identified and we avoid duplicate relationships and duplicate maybe entities. So to conclude, we contribute, our study contribute with a data set for maybe for business-to-business analysis. But the main contribution is the ability to automate the process of the knowledge graph construction in the domain of business-to-business networking. And also we had additional experiment on using what we're taught to do some sort of unsupervised version classification. And also we provide guidance on how we can use dimensionality reduction to reduce the size of what vectors without compromising the performance too much. And coming back to the reason of this research, how we can practically apply our findings in the real world. So, for example, if we're able to build a knowledge graph based on the news, we can identify click in the graph. So click can help us maybe see a click in the graph is a tightly connected group of nodes. So it can also give us an idea of some business conglomerates. So if we see a couple of businesses that are usually very tightly connected, it might also indicate that this is a business conglomerate. We can also use graph algorithm to identify influencing business stakeholders like a very influent company, organization, or a very influent person, or even an influential product. And we can also infer missing information. Like for example, if we go through the text and there is some missing characteristic of an entity such as an organization, we can use non-level graph learning to predict those properties. We can also do link prediction that might actually help us suggest partnerships. So if we use the link prediction graph network and it suggests a link, maybe we can suggest like some sort of partnership between companies and people and so on. So those are the application and every sort of achievement with it, and all the code is available publicly. So I think in the future we can consider the temporal evolution of the knowledge graph, so we can separate the news as chronologically, and then we can see how the knowledge graph evolved over time. Then trying to make some inference in the future what might happen. And yes, so based on this study, we can also build something on top of it, that may be a website or some sort of API that will help this research be used in the real world. And this research can also be spread to adjacent domains such as political and social domains to see maybe what type of influential person is linked to any type of like political cause or social cause and so on. So this will be the end of our presentation. Our study is the main goal was to support companies or business people, business to find partnership in the market they don't always understand. So the initial idea came when we produced a joint a program where especially in Japan, JICA was trying to help Japanese business to go in overseas market. So for example, Southeast Asia market or African market. But usually the Japanese, they don't really know what's happening or how this market is structured. So it's very difficult for the Japanese businessmen to understand and make a move. So that's why we came up with this idea of maybe we'll build something that can automatically identify and link business, and then from that people can get some sort of idea of what the business market looks like. And yes, so we provide the data set and make some analysis, and also propose some sort of enterprise method for relation classification. We studied two-dimensional reduction of the web vectors and propose another basic pipeline to build knowledge graph from